Hey guys, here's a video to help with the improper integral basics. So an improper integral essentially usually looks something like this. You've got some function, let's say 1 over x squared. Let's let that be our function. And the goal would be to try to find the area under something like that from, say, 1 going off to infinity. So if you're thinking about area, from 1 to 5, no big deal. You just stop at 5 and we can calculate that. You go to 10, go to 20, etc. But this is asking, what about if you're going off to infinity? So what if you're trying to evaluate an integral that looks like this? That's the main idea. So this is called an improper integral, since our limits basically force us into talking about an infinite, what seems like an infinite area. It doesn't have to actually go off to infinity, and I'll show you another example in a minute, but this is essentially the question we're trying to answer. So it doesn't actually take much to be able to evaluate this. We just need to sort of think of it in terms of a limit instead. Just like when we were doing limits back in the day, we had values for a lot of limits. Even if there was a hole in the graph, we could still find a limit as long as the graph approached the same value from both sides. So it may not have value there, but it definitely has a limit. Yeah, if I keep going with this graph, it seems like we're adding on area each time we go. It just ends up being infinitely small that we do find a value for this integral using a limit. So you would literally just take a limit, and they usually use the letter t as t goes to infinity, and just basically substitute the infinity for t and apply everything we know about integrals to now this integral, and just bring the limit along for a ride until we're ready to actually apply it. So if I do this one correctly, it would be the limit as t goes to infinity for, let's see, 1 over x squared, that's x to the negative 2. So negative 1 over x evaluated from 1 to t. So this would be the limit as t goes to infinity for negative 1 over t minus negative 1 over 1, if I just write everything out. Well, as t goes to infinity, this whole thing right here, this negative 1 over t goes to 0. So I'm left with positive 1, sometimes written just 1. Okay, so this integral actually does have a value. The value essentially for the area under this curve from 1 to infinity is 1. Okay, so it's kind of a neat way to deal with what seems like an infinite amount of area. Okay, so that's the main idea. Then we sort of tried, what about something that looks a lot like that? Almost the same picture, really. Obviously, I'm not drawing it to scale. But what if this was 1 over x? And I asked you the same question, going from 1 to infinity. Well, you might think, oh, probably 1 again, right? Well, one way to find out. Let's take the limit as t goes to infinity of 1 over x. And if we evaluate that, t goes to infinity. The antiderivative of 1 over x, that's our natural log. So this is going to be natural log absolute value of x evaluated between 1 and t. Well, t is positive already for this one, so I don't really have to worry about the absolute value. But I'll just mention it just in case. This is going to be ln infinity, ln t. Sort of gave away the punchline there. ln t minus ln 1. And as t goes to infinity, well, natural log of big numbers that just keep getting bigger are still big, goes off to infinity. So this goes to 0 is great. Ln 1 is 0, but this is still infinite. So this limit is infinity, which means that this particular integral we call divergent. Or this integral diverges. It's divergent. The other one, sorry, I should probably mention that. If it actually approaches a particular value, we say that the integral is convergent, or the integral converges, depending on the tense you're using. So this converged to 1. This diverged because the actual integral went off to infinity. The limit went to infinity. Okay? So the main idea here is this improper integral idea is using limits to evaluate integrals that we wouldn't normally be able to evaluate simply because infinity is involved somehow. All right? So an example where you might not catch it right away, but it's still the same idea is, what if we were to take, what if we were to look at this integral, 2 to 5 of 1 over the square root of x minus 2. You know, at first glance, you look at that, you're like, oh, that's like every other integral problem I've done. I'll try to come up with some trick to get it, you know, use, reverse power rule, maybe some U substitution, or, you know, by parts, whatever trick we've learned. You look at this, you're like, oh, it's only from 2 to 5, no big deal. But if you look closely, if you think of this graph, and I'm starting this at 2, right? 1 over square root of x minus 2 is not defined at 2. So there's an asymptote there. So there's no infinity showing. However, the limit as x approaches 2, and obviously I'd have to think about 2 from the right because I'm going from 2 to 5, is infinity. Okay, it's positive infinity. So there's an infinity hiding in here, but not in the way you may have thought. The good news is the process is exactly the same. So the limit as t approaches 2, I'm going to be specific now because I'm only going from the right. That does matter, so make sure you pay attention to that. And I know it's from the right again because I'm between 2 and 5. If I'm between 2 and 5, then my 2 values are a little bit bigger than 2. Okay, if I start less than 2, well then that would imply that I'm using a number lower than 2. So this becomes the integral 1 over square root of x minus 2 from t to 5. And now I can go through and find this antiderivative, use my limits, and then take the actual limit after that. So to get this antiderivative, you know, your comfort level hopefully is pretty good with something like this where you don't really need to use a U substitution. I'm hoping you're looking at this and thinking of that as, you know, x minus 2 to the negative 1/2. That would make this a lot easier. And since the coefficient of the x is just 1, I don't even have to worry about a reverse chain rule. But if you're ever not sure, there's nothing stopping you from doing a U substitution here and then going from there. I just think it takes longer, so I generally don't do it anymore. You know, when we started, no big deal, but I want you guys to try to get as efficient as possible doing these. So I look at this and I see that. And to me, that's a reverse power rule. Reverse chain rule kicker is negated because it's just a 1, and the antiderivative is a little bit easier to deal with. So this is 2 from the right. This is going to be 2 x minus 2 to the positive 1/2 from t to 5. The 2 came from, again, if you do the reverse power rule here, it's x minus 2 to the positive 1/2 over 1/2, which becomes 2. So do this out as you need to. However you want to do it, you should get here. Okay, if that's causing you a problem, well, then we'll work on that too, but that's not for this video. So this is where we're at. So this becomes the limit as t goes to 2 from the right of 2. 5 minus 2 to the 1/2 minus 2 times t minus 2 to the 1/2. And now it's just a matter of cleaning it up. This limit as t approaches 2 has no effect on this part, but completely is affected here. Or completely has an effect here, excuse me. If t is approaching 2 from the right, well then this number is a little bigger than 2. Minus 2 essentially is close to 0. Square root, of course, is still 0. Times 2 is still 0. This whole thing goes to 0. And all I'm left with is 2 square root of 3. So this does converge. This integral converges, and it's 2 radical 3. And that's basically it. Now they can get more complicated, and usually by more complicated, it's just that this is complicated. Maybe this requires a U substitution. Maybe this requires integration by parts. Maybe it requires integration by partial fractions. Maybe it's got some trig in it. There's all sorts of different things they can do now, but it opens you up to the possibility of having a limit involved instead if this is truly an improper integral. All right. Hopefully that'll get you off and running. And if you need any help, any additional help, just let me know. And I will see you guys later. Bye.